Jupiter's wind models stopped matching reality the moment the Great Red Spot crossed a size threshold no one had ever tested, and the error showed up as a drift in cloud motion that should not have existed at all. In telescope logs from Earth observatories, the Great Red Spot is already visibly tighter, its edges pulling inward while surrounding cloud bands begin sliding past it like loosened belts. The consequence is immediate inside the data stream. Forecasted jet speeds no longer line up with actual motion, and the mismatch keeps growing after every observation cycle. The first reaction inside the tracking networks was simple recalibration. But the visual anchor refuses to behave like a normal storm. In the time-lapse overlay of Jupiter's southern hemisphere, the Great Red Spot is shrinking from a stretched oval into a compact, rotating knot. The surrounding cloud bands do not ignore it. They reorganize around it, as if something structural is being removed. That shrinking oval is not just changing size. It is changing how the entire hemisphere moves. At first, this is treated as a measurement refinement problem. Instruments are checked, filters adjusted, historical plates remeasured. The visual anchor appears again in older observations, now with a new meaning. Decades ago, when the Great Red Spot was wider than 3 Earths, it was not just a storm. It was a boundary condition embedded inside Jupiter's atmospheric system, a fixed point in motion, a stabilizer hidden in plain sight. But that interpretation begins to fail when the shrinking continues past known thresholds. The Great Red Spot contracts further in the overlay sequence, becoming denser, faster, more circular, and something else changes with it. The surrounding eddies, once feeding into it, begin to detach. They stop merging. They slide past it instead. The system loses its old coupling behavior. That is the first rupture in understanding. And that is where the real problem begins. Because the same visual anchor, the shrinking Great Red Spot, now reveals something no model accounted for. It was not just a storm consuming energy, it was regulating flow across Jupiter's equator. When it was large, it pulled surrounding turbulence into a structured exchange. When it shrinks, that exchange collapses. The planet's wind field does not simply adjust, it reorganizes into something less predictable, less anchored. The time-lapse overlay now shows the Great Red Spot as a tight, almost circular vortex, smaller than any historical baseline. But the consequence is no longer local. Jet streams on either side begin shifting out of phase. Bands that once moved in coordinated rhythm start slipping. The visual anchor returns again, and this time it carries a different implication. The storm is no longer controlling its environment. It is losing the ability to hold it together. Midway through the observation records, something larger emerges. Jupiter's equatorial system begins to show structural drift, not turbulence, drift. Long-term displacement of flow boundaries that were assumed to be stable for over a century. The Great Red Spot, still visible in the shrinking overlay, is now directly linked to these boundaries. When it weakens, the entire system loses a reference point. Models built on that reference start failing across multiple latitude bands at once. The visual anchor appears again during this phase, now a tight red circle against reorganized cloud belts, but the interpretation has shifted again. It is no longer the largest storm on the planet. It is a missing piece of structure that used to lock everything else in place. And without it at full scale, Jupiter's wind system behaves like a machine losing its central bearing. Then the pressure escalates. Observations from later imaging runs show that the Great Red Spot no longer feeds on surrounding eddies the way it used to. Instead of absorbing them, it repels them. That change removes the last stabilizing interaction between the vortex and the equatorial flow. The visual anchor, now extremely compact in the overlay sequence, becomes almost isolated. A rotating object surrounded by flow that no longer integrates with it. At this stage, prediction systems begin failing in a specific way. Not by error margin, but by structural mismatch. The models still assume coupling where no coupling exists. Each update produces less accurate forecasts than the last. and the reason traces back to the same image. The shrinking great red spot is no longer behaving like a long-lived storm. It is behaving like a decaying constraint inside a dynamic system that depended on its size. And then the largest shift arrives. When the overlay reaches its most recent state, the visual anchor is small, tight, and fast. But the surrounding atmosphere has reorganized into new band interactions that do not match any historical pattern. The equatorial system is no longer anchored by a single dominant vortex. It is now distributed, unstable, and less predictable at long timescales. The collapse is not of the storm itself, but of what the storm used to guarantee. What changes here is not visibility. It is meaning. The same great red spot that once appeared as a massive oval in 19th century telescope drawings is now understood as something far more critical. A structural regulator inside Jupiter's wind system. Its size was not a detail. It was the condition that made the rest of the atmosphere behave consistently. The final visual anchor returns one last time in the overlay. Small, dense, still rotating, but now it is clear what has been lost. Jupiter's equatorial winds no longer have a fixed organizing center. The system that once looked stable was partly stable because of it. And as that realization locks in, the earlier images change again. The massive ancient oval was not just a storm in the sky. It was holding the sky in place. The great red spot did not only shrink. It released Jupiter's balance.